Introduction. Come on, Dad. Let's get on the balloon. Easy, Rohit, easy. Yippee! It is going up now. We are flying like a bird. Dad, I want to ask you something. Yes, Rohit, tell me. How it gets into the air? In this, we use gaseous fuel to heat up the air in the envelope to move the balloon off the ground and into the air. Okay, Dad. One more thing I want to share with you, that the gaseous state has no definite shape. In this lesson, you will learn gaseous and liquid states of matter. Objectives. At the end of this lesson, you will be able to explain intermolecular forces, distinguish between solid, liquid and gaseous state, state the gas laws, state ideal gas equation, state Dalton's law of partial pressures, describe kinetic molecular theory of gas, distinguish between ideal gases and real gases, discuss vapor pressure of liquids, define surface tension and viscosity. Intermolecular forces. The forces of attraction between molecules which keep molecules together are called intermolecular forces. The energy due to force of attraction between molecules is called molecular interactional energy. Molecular interactions lead to intermolecular attractive and repulsive forces. Attractive intermolecular forces are also called van der Waals forces, dispersion forces or London forces. Electrons are symmetrically distributed around the atom most of the time, but at any instant there may be some asymmetry in the distribution of electrons around the nucleus, resulting into an electric dipole. This dipole produces an electric field which distorts the electron distribution of neighboring atom or molecule, which also becomes dipole. These two dipoles will attract, and these forces of attraction between them are called dispersion or London forces. It occurs in non-polar molecules and even noble gases. For example, one atom has symmetrical distribution and the other has unsymmetrical distribution, and the atom with unsymmetrical distribution distorts the electron distribution of the other atom, results in a force of attraction. Dipole-dipole forces. These are the interparticle forces among the polar molecules. These forces arise due to electrostatic interactions between the oppositely charged ends of permanent dipoles. The positive end on one molecule attracts the negative end of the other molecule and vice versa. These charges are shown by delta. Dipole-induced dipole forces. It is the force of attraction between molecule having permanent dipole moment and other molecules having zero dipole moment, like CH4, CCl4, BF3, SO3, etc. For example, a polar molecule such as HCl can induce a dipole in an argon atom by distorting the electron cloud. An electrostatic attraction exists between the ion or permanent dipole and the induced dipole. The intermolecular force is called a dipole-induced dipole attraction. Hydrogen bond. Hydrogen bond is defined as the electrostatic force of attraction which exists between the covalently bonded hydrogen atom of one molecule and the electronegative atom of the other molecule. The hydrogen bond is represented by dotted line. For example, in case of hydrogen fluoride, the hydrogen bond exists between H atom of one molecule and fluorine atom of another molecule. Hydrogen atom should be bonded to a highly electronegative atoms such as fluoride, oxygen or nitrogen. Larger the electronegativity of the other atom, greater is the strength of hydrogen bond. Thermal energy. The energy which moves the molecules apart is called thermal energy. It is defined as the energy possessed by matter by virtue of its temperature and is also a measure of thermal motion or movement of molecules. Intermolecular forces versus thermal interactions. The three states of matter are, in fact, the result of competition between the molecular interaction energy and thermal energy. In solids, the molecular interactions are very strong and the molecules possess low thermal energy. In liquids, a fine balance exists between attractive forces and thermal energy. Increase in temperature further increases the thermal energy, and ultimately a stage reaches when the molecules fall apart and behave almost as independent entities. This stage refers to gaseous state. Gaseous state. The state of matter in which the molecular forces of attraction between the particles of matter are minimum is known as gaseous state. Gases completely fill the container that holds them. Characteristics of gases. Gases or their mixtures are homogeneous in composition. Gases have very low density due to negligible intermolecular forces. Gases exert pressure. Gases do not have definite shape and volume like solids and liquids. Thermal energy of gases is much greater than molecular attraction. The gas laws. Boyle's law. Pressure-volume relationship. The volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. Mathematical interpretation of the law. Volume is inversely proportional to pressure at constant temperature and mass. V is equal to K into 1 by P, where K is constant of proportionality. PV is equal to K is equal to constant. Let V1 be the volume of given mass of a gas having pressure P1 at temperature T. Now, if the pressure is changed to P2 at same temperature, then the volume changes to V2. The quantitative relationship between four variables P1, V1, P2 and V2 is P1 V1 is equal to P2 V2 at constant temperature and mass. Graphical representation of Boyle's law. It shows the plot of V versus P at a particular temperature. It shows as P increases, V decreases. It shows the plot of PV versus P at particular temperature. It indicates that the PV values remains constant in spite of a regular increase in P. The curve obtained by plotting PV against P at a particular temperature is called isotherm. The higher curve corresponds to a higher temperature. It shows the variation of P against 1 by V. The straight line indicates that 1 by V regularly increases with the increase in P. Charles' law. Temperature-volume relationship. Statement. The volume of a given mass of a gas increases or decreases by 1 by 273.15 of its volume at 0 degrees Celsius for each degree rise or fall of temperature provided pressure is kept constant. If V0 is the volume of a given mass of a gas at 0 degrees Celsius, then V1, the volume of a gas at 1 degree Celsius, is equal to V0 into 1 plus 1 by 273.15. Vt, the volume of gas at T degrees Celsius, is equal to V0 into 1 plus T by 273.15. The lowest possible temperature at which all the gases are supposed to occupy zero volume is called absolute zero. A scale of temperature based upon this choice of zero is called absolute scale of temperature. This scale is also known as Kelvin scale of temperature. Charles' law can also be stated as the volume of the given mass of a gas at constant pressure is directly proportional to the temperature on Kelvin scale. Volume is directly proportional to the temperature at constant pressure and mass. V is equal to K1T, where K1 is constant of proportionality. Let V1 be the volume of a certain mass of a gas at temperature T1 and at pressure P. If temperature is changed to T2 keeping pressure constant, the volume changes to V2. The relationship between four variables V1, T1, V2 and T2 is V1 by T1 is equal to V2 by T2 at constant pressure and mass. Graphical representation of Charles' law. Each line of the volume versus temperature graph is called isobar. Gay-Lussac's law. Pressure-temperature relationship. This law states that pressure of a given mass of a gas is directly proportional to the Kelvin temperature at constant volume. Mathematically, pressure is directly proportional to temperature at constant volume and mass. P by T is equal to K2. Let P1 be the pressure of a certain mass of a gas at temperature T1 and having a volume V. Now, if temperature is changed to T2 at the same volume so that the corresponding pressure becomes P2, then according to the law, P1 by T1 is equal to P2 by T2. Volume and mass remains constant. Graphical representation of Gay-Lussac's law. Each line of this graph is called isochore. Avogadro's law. Volume-amount relationship. This law states that equal volume of all the gases under similar conditions of temperature and pressure contain equal number of molecules. Mathematically, volume is directly proportional to the number of moles of gas. V is equal to K3N, where K3 is constant of proportionality. The number of molecules in 1 mole of gas is 6.023 into 10 raised to the power 23 and is known as Avogadro's constant. The number of moles can be defined as N is equal to M by M, where M is equal to mass of a gas under investigation and M is equal to molar mass. Ideal gas equation. A gas which obeys the gas law strictly is called an ideal gas. The combination of Boyle's law, Charles' law and Avogadro's law leads to the development of the equation which we called ideal gas equation. It is given as PV is equal to nRT, where R is the constant of proportionality which is independent of the amount as well as nature of gas and is known as universal gas constant. Its value is 8.31 joule per Kelvin per mole. P is the pressure of fixed amount of gas. V is the volume of fixed amount of gas. T is the temperature of fixed amount of gas. N is the number of moles of gas. If temperature, volume and pressure of a fixed amount of a gas vary from T1 V1 and P1 to T2 V2 and P2, then we can write P1 V1 by T1 is equal to P2 V2 by T2. This equation is called combined gas law. Standard temperature and pressure, STP. For gases, the standard temperature is taken as 0 degrees Celsius or 273.15 Kelvin and standard pressure as 1 bar or 10 raised to the power 5 Pascal. At STP, molar volume of an ideal gas or a combination of ideal gases is 22.71098 liter per mole. Another unit for pressure measurement is torr. 1 torr is equal to 133.322 Pascal. Example: a sample of nitrogen gas occupies a volume of 320 cm cube. At STP, calculate its volume at 66 degrees Celsius and 84,000 Pascal pressure. Solution: given P1 is equal to 10 raised to the power 5 Pascal, P2 is equal to 84,000 Pascal, V1 is equal to 320 cm cube, T1 is equal to 273.15 Kelvin, T2 is equal to 66 degrees Celsius is equal to 66 plus 273.15 Kelvin is equal to 339.15 Kelvin. We have to find V2. So, according to gas equation, P1 V1 by T1 is equal to P2 V2 by T2. Hence, V2 is equal to P1 V1 T2 by T1 P2 is equal to 10 raised to the power 5 into 320 into 339.15 divided by 273.15 into 84,000 is equal to 473 centimeter cube. Density and molar mass of a gaseous substance. Molar mass of the gas can be found by the formula M is equal to D into R into T by P, where D is equal to M by V is the density of the gas, M is mass of gas, V is the volume of the gas, R is the universal gas constant, T is the temperature of the gas, P is the pressure of the gas. Dalton's law of partial pressures. At constant temperature, the pressure exerted by the mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressures which each gas would exert if present alone is the same volume. The individual pressures of gases are known as partial pressures. If P is the total pressure of the mixture of non-reacting gases at temperature T and volume V and P1, P2, P3 represents the partial pressures of the gases, then P is equal to P1 plus P2 plus P3 plus so on, where T and V are constants. Suppose we have 3 containers of capacity 1 liter each, one containing X mole of nitrogen, the other Y mole of oxygen, and third having a mixture of X moles of nitrogen and Y moles of oxygen. All the 3 containers are kept at the same temperature. Now, if the manometer attached to first container shows a pressure P1 and that attached to second container shows a pressure P2, then pressure in the third container is P1 plus P2. The pressure of the water vapors is a constant at a particular temperature and is known as aqueous tension at that temperature. Pressure of a dry gas can be calculated by subtracting aqueous tension from a total pressure. P dry gas is equal to P minus aqueous tension. Partial pressure in terms of mole fraction. Mole fraction is the ratio of the number of mole of the component to the total number of moles. Consider a mixture of two gases A and B with PA and PB as their respective partial pressure in a vessel of volume V at temperature T. Then, PA is equal to NART by V. PB is equal to NBRT by V. The partial pressure of gas A and B can be expressed as PA is equal to XA into P. PB is equal to XB into P, where P is the total pressure, XA and XB are the mole fraction of gas A and B. Thus, partial pressure of a gas in a mixture is equal to the product of its mole fraction and total pressure of the mixture. Kinetic molecular theory of gas. Postulates of kinetic theory of gas are: all gases are made up of very large numbers of extremely small particles called molecules. The molecules are separated from one another by large spaces so that the actual volume occupied by the molecules is negligible as compared to the total volume of the gas. The molecules are not at rest but possess rapid random motion. During this motion, they collide with one another and also against the walls of the container. The pressure of the gas is due to the bombardment of the gas molecules against the wall of the container. The collisions of the molecules with each other and with the walls of the container are perfectly elastic. That is, there is no loss or gain of kinetic energy. However, there may be redistribution of energy during such collisions. There are no attractive forces between the molecules of the gas. They are completely independent of each other. At any instant, different molecules possess different velocities and hence different energies. However, the average kinetic energy of the molecules is directly proportional to the absolute temperature. Behavior of real gases. Deviation from ideal gas behavior. We show the deviation of real gas from the ideal behavior by introducing compressibility factor. Z can be expressed as Z is equal to PV by nRT. In case of ideal gas, PV is equal to nRT. Hence, Z is equal to 1. In case of real gas, PV not equals to Z nRT. Hence, Z not equals to 1. Thus, in a case of real gas, the value of Z can be less than 1 or greater than 1. When Z is less than 1, it refers to negative deviation. It implies that the gas is more compressible than expected from ideal behavior. When Z greater than 1, it refers to positive deviation. It implies that the gas is less compressible than expected from ideal behavior. Cause of deviations from ideal behavior is due to two faulty assumptions of kinetic theory of gas, that are: the volume occupied by gas molecules is negligibly small as compared to the total volume occupied by the gas. The forces of attraction between gas molecules are negligible. Van der Waals equation. In 1873, Van der Waals modified the gas equation to make it applicable for real gases as well. That is, P plus An square by V square into V minus Nb is equal to nRT. The constants A and B are also called Van der Waals constants. Liquefaction of gases. Liquefaction of gas can be achieved by decrease of temperature and by increase of pressure. Concept of critical temperature. At low temperature 13.1 degrees Celsius, CO2 exists as gas at low pressure as shown by point A. As the pressure is increased, the volume of gas decreases along the curve AB. At point B, liquefaction starts. Hence, volume decreases rapidly along the line BC. At the point C, the liquefaction is complete. Now further increase of pressure has very little effect upon the volume because liquids are very little compressible. Hence, a steep curve CD is obtained. Thus, along the portion AB, carbon dioxide exists only as gas, along the portion CD only as liquid, and along the portion BC, the liquid and the vapor are in equilibrium with each other. The isotherm EFGH at 21.5 degrees Celsius is smaller to that at 13.1 degrees Celsius, except that the horizontal portion over the liquefaction occur is shorter. In the isotherms above 31.1 degrees Celsius, the horizontal portion completely disappears. This shows that above 31.1 degrees Celsius, the liquefaction of the gas does not take place at all. However, high pressure may be applied. The point X is called critical point and temperature corresponding to point X is called critical temperature. The critical temperature of the gas may be defined as the temperature about which it cannot be liquefied by application of pressure. The pressure required to liquefy the gas at critical temperature is called critical pressure. The volume of 1 mole of the gas at critical temperature and critical pressure is called critical volume. Liquid state. In liquid state, particles are close together and have quite strong intermolecular forces. The liquids are neither rigid nor do they possess definite shape. Vapor pressure. The vapors of liquid collide with each other as well as with the walls of the container and exert pressure. The pressure exerted by vapors on the wall of the container is called vapor pressure. Vapor pressure is directly proportional to the temperature. It is independent of the amount of liquid. The pressure exerted by the vapor when they are in equilibrium with liquid in a closed container is called equilibrium vapor pressure. The temperature at which the vapor pressure of a liquid is equal to external pressure is called boiling point of liquid. Surface tension. A molecule within the bulk of liquid is uniformly attracted in all directions by the neighboring molecules. Therefore, the net force of attraction acting on such a molecule is almost zero. However, a molecule at the surface of liquid has no upper molecules to participate in attraction. This creates imbalance of forces at the surface of the liquid. Consequently, the molecules at the surface experience a resultant inward pull. For a plane surface, the force acting parallel to the surface and perpendicular to a line of unit length anywhere in the surface is called surface tension. It is represented by gamma and its unit is dynes per centimeter or Newton per meter. In order to increase the surface area of the liquid, some energy has to be supplied against the inward pull. This is referred to as surface energy. Thus, surface energy is the energy required or work required to be done to increase the surface area of the liquid by a unit amount. It is expressed in joule per meter square or Newton per meter. Viscosity. Viscosity implies resistance to flow. It is well-known fact that some liquids such as honey, castor oil, glycerine, etc. flow slowly, whereas other like water, petrol, ethanol, etc. flow rapidly. This means that every liquid has some internal resistance to flow, which is referred to as viscosity. Liquids which flow slowly are said to be more viscous than the liquids which flow rapidly. The force of friction F between two cylindrical layers, each having area A square centimeter separated by a distance x centimeter and having a velocity difference of nu centimeter per second, is given by F is equal to eta A nu by x, where eta is the coefficient of viscosity. Now, if A is equal to 1 centimeter square, nu is equal to 1 centimeter per second and x is equal to 1 centimeter, then F is equal to eta. Thus, coefficient of viscosity may be defined as force of friction required to maintain velocity difference of 1 centimeter per second between two parallel layers 1 centimeter apart and having an area of 1 centimeter square. SI unit of viscosity is Newton per meter square second or 1 poise. Did you know? Graphite enters different states of matter in ultra-fast experiment. For the first time, scientists have seen an X-ray irradiated mineral go to two different states of matter in about 40 femtoseconds. A femtosecond is 1/400th of a second. Ultra-fast phase transitions from solid to liquid and plasma states are important in the development of new material synthesis techniques, ultra-fast imaging and high energy density science. Summary. Let us summarize what we have learnt. The force of attraction between molecules which keep molecules together are called intermolecular forces. Hydrogen bond is defined as the electrostatic force of attraction which exists between the covalently bonded hydrogen atom of one molecule and electronegative atom of the other molecule. The energy which moves the molecules apart is called thermal energy. Boyle's law states that the volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. PV is equal to K is constant. Charles' law states that the volume of a given mass of a gas at constant pressure is directly proportional to the temperature on Kelvin scale. V by T is equal to K1 is constant. Gay-Lussac's law states that pressure of a given mass of a gas is directly proportional to the Kelvin temperature at constant volume. P by T is equal to K2 is constant. Avogadro's law states that equal volumes of all gases under similar conditions of temperature and pressure contain equal number of molecules. V by N is equal to K3 is constant, where N is the number of moles of gas. Ideal gas equation is given as PV is equal to nRT, where R is the universal gas constant. Dalton's law of partial pressures states that at constant temperature, the pressure exerted by a mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressures which each gas would exert if present alone in the same volume. Liquefaction of gas can be achieved by decrease of temperature and by increase of pressure. The pressure exerted by vapors on the walls of the container is called vapor pressure. For a plane surface, the force acting parallel to the surface and perpendicular to a line of unit length anywhere in the surface is called surface tension. It is represented by gamma and its unit is dynes per centimeter or Newton per meter. Every liquid has some internal resistance to flow, which is referred to as viscosity.